Okay, hello everyone. Welcome back to SFC's first ever Student Research Festival. We are hosting three graduate or upper year undergraduate students this week to share their cutting edge research in natural resources. This festival is an opportunity for students to share their knowledge in a friendly, low pressure environment with other students who are passionate about balancing the needs of people, planet, and prosperity. This is our first research event, but we hope to host more, so please follow SFC on social media at Students for Canada on Instagram, LinkedIn, and Facebook to hear more about our future events. For those of you who are just seeing SFC for the first time, we are an advocacy group made by students and young professionals for students and young professionals who believe that Canada can have a strong future in resources, the economy, and the environment. We are fortunate to have such fantastic support from a variety of students and young professionals, Robin and Raiya included. Today's research festival stars Robin Dhaliwal and Raiya Hassan. Robin is a final year chemical engineering student at the University of Alberta. She is active, curious, social, and self motivated, and is also passionate about making a positive impact on society. This combination led her to her passion for creating helpful solutions. She is a Dean's Research Award student for several semesters for her research focused on electrostatic atomization. Raiya is also a final year chemical engineering student at the University of Alberta. She is interested in research in sustainable practices and sustainable resource management. Her previous work experiences are working in research on partial upgrading of bitumen and research in uremic toxic adsorption in UTI patients as a research assistant at the UofA.
So, hello everyone. As Gary said, I'm Raiya Hassan.
Hello, my name is Robin, and we both are final year chemical engineering students, as Barry mentioned, at the University of Alberta. And today we will be talking about our research, which focuses on harnessing solar energy through energy crops and then converting it into a biofuel. So, for the agenda today, in our presentation, we will be going to cover the problem statement, the background, proposed solution, different applications of the biocrude, as well as the byproducts, and its impact on the three P's: people, planet, and prosperity.
So, just to talk about the problem. So, as we all know, a big problem in the world has been the increase in global warming for the last few years. This is a very well talked subject. And we know that one of the biggest reasons is the emission of greenhouse gases, especially carbon dioxide. Just to give you all a perspective, the carbon dioxide concentration has increased by about 37% in the last 5 years. It is believed that the temperature will increase by a further 1.1 to 6.4% in the next century. Now, to combat this issue, different countries have been trying to find out different ways to find solutions. Canada, particularly, has set a net zero emission target by 2050. And the province of Alberta's Renewable Electricity Act targets to have 30% renewable electricity in 2030, which equates to an additional 4,000 megawatts of energy to the grid. Currently, around 92% of Alberta's electricity is produced from natural gas, while energy sources such as wind, solar energy, biomass produces the remaining 8%. There are some ways to bring renewable energy use in the world. For example, we're using electric cars now. However, the problem is this electric car is being charged by electricity, and this electricity is being produced by fossil fuels. So overall, the problem is not really solved. So that is why we thought that a good source of renewable oil would be one of the best solutions. And we call this bio oil, and it can be produced from different sources like feedstocks like sewage sludge from algae and others. And Robin will give you a little bit of a background.
As we all know, the sun provides a sustainable energy source for the Earth. However, there are intermittency concerns with solar radiation because of weather patterns and the Earth's rotation. Therefore, it is critical to store solar energy as a fuel to allow for it to be continuously available at all times to meet our societal needs. This includes times when the sun is not shining or when minimal solar radiation is present, such as during night or when the sun is obscured by clouds or in the wintertime. Currently, the conventional pathway to utilize solar energy is mostly through solar panels. However, you will be surprised to know that solar panels are only 12 to 18% efficient, and they are also very expensive. But with our population and consumption, this would mean hundreds of thousands of solar panels. To give you a perspective, we need 10 solar panels to charge just one Tesla. That is why solar radiation is a sustainable energy source that is only effective for us when converted to a fuel which can be upgraded and stored to supply energy continuously. What we are proposing here is to capture the intermittent sunlight to grow energy crops and produce biocrude from it, which can be further processed to give different kinds of lighter fuels and electricity. Now, let me talk about the proposed solution. For the HTL process, HTL hydrothermal liquefaction, which we'll be talking about more in the upcoming slides, we looked at a couple of different energy crops, including switchgrass and miscanthus. You might have heard of them because they're quite popular. Talking about switchgrass, it is more adaptable to Alberta's prairie soils, and it also does not need to be regrown annually. So we can leave some of the plant in the soil and harvest from the top. This will regrow next year, leaving enough batch for the next year so that it does not need to be regrown. And that 6 inches that we leave, it also prevents it from the harsh Albertan winter cold. Miscanthus, on the other hand, is considered to be an invasive species and is highly flammable, posing a fire hazard in hot Albertan summers. We have about 3.58 million hectares of marginal land in Alberta, which can be used for crops to reduce land competition between food and energy crops. Using the HTL process, we propose to convert these crops into biocrude. We can obtain bio-oil from biocrude and burn it to produce electricity. Moreover, biocrude can be fractionated to get biodiesel or jet fuel to replace conventional diesel in car and other automobiles. This is still something to be explored because the bio-oil tends to be more corrosive than normal fossil fuels due to their higher acidity. This could be harmful for the general make of cars that we have in the market right now. Moreover, bio-oil has some moisture content in it, which can freeze in Alberta in colder winters, which could also mean blockage in the car engines. So we are mostly looking into producing bio-oil to be consumed within the matter of weeks. This way, the carbon dioxide released during the combustion of oil to produce electricity could be captured by the plants that we have in the fields, so that the net carbon dioxide emission would be within the acceptable range, if not zero. Now, process overview will be talked by Raiya.
Okay. So how does the hydrothermal liquefaction plant work? So it is a process by which biomass can be converted into bio-oil using hot pressurized water. So initially, feedstocks are fed into this bio-oil, this HDL reactor, and is mixed with water at high temperature and pressure. Now, the good thing about HDL is that the feedstocks can be different things. Can be algae, food waste, sludge, manure, lignocellulosic plants, and stuff. So just going into a little bit detail on the different kind of feedstocks and what we get from them. For example, sewage sludge. So sewage sludge disposals from municipal and industrial wastewater plants, and it has always been a concern to get rid of these. In the recent past, many countries have been focusing on resource reuse and environmentally friendly disposal of sewage sludge. However, they can, for example, in the industrial ones, there's a lot of chemical wastes, and you can't just get rid of them as easily as just like dispose it into the water or something like that. So in order to help with the waste management, we can use sewage sludge in making bio-oil. Raw sewage sludge has high volatile organic content and favorable heating value for conversion into fuels and biochemicals. However, a bit of a problem is the controlling of the products of the sludge. So different kind of wastes have different kind of organic matter in it. And given the different chemical compositions, they provide different kind of oil with different heating values, different combustion values. Another good source is hemp. So industrial hemp has the potential to be an energy crop comparable to quinoa, switchgrass, and other biomass sorghum or wood. Bio-oil can be produced from both the stems and the grains of the plants. Results showed a predicted ethanol yield of about 82 gallons per dry ton hemp stems. A comparative cost analysis indicated that industrial hemp could generate higher per hectare gross profit if both hemp seeds and the stems are used for biooil compared to any other energy crops. Hemp grows fast, it's disease resistant, and is also cheap to grow. Research indicates that hemp absorbs more carbon dioxide and converts energy from the sun into biomass through photosynthesis compared to any larger plant within its short growth cycle. However, the problem comes with the use of hemp. So, hemp is a very important food source, and it's also used for many other products like paper feed, oil, foods like energy bars, and also things like reusable bags, animal bedding, etc. So, just using hemp only for oil can be difficult because, like, farmers can be selling these for it's different parts for different things, and that could harm the economic visibility of the market and also decrease the market production of other products. Thus, we thought that using energy crops is the best when looking into the carbon dioxide abatement option and also about the economic feasibility and sustainability. Now, the typical operating conditions for HDL process are moderate temperatures of about 250 to 374 degrees Celsius and high pressures like 4 to 22 megapascal. However, the temperature and higher temperature and pressure conditions could give a higher yield and high quality product. However, this is not realistic in large scale. So we keep it around 250 to 374 degrees Celsius. The biooil is basically put in this cylindrical reactor, and it's allowed to sit there under the influence of a catalyst where the breakdown of molecules turn them into feed into biocrude, and the residence time is around 15 minutes. Typical products of HDL are char, gas, aqueous phase extract, and high energy intensity biocrude oil, which can then be separated through further filtration. These biocrudes and gas are then taken to the cogen plant where it is burned to make electricity. The water that we have added in the beginning with the feed is then extracted in the aqueous phase, and then taken into a water treatment plant, and then this water can also be recycled.
Let's talk about the applications of biocrude as well as the other byproducts that we made in this process. Starting with the biocrude. Biocrude is the main product of the HTL process. This oil is similar to petroleum crude, which can be further hydrotreated to reduce oxygen content and saturated double bonds. If the bio-oil cannot be used immediately, it must be stored at low temperatures to minimize its degradation. The next one is the aqueous phase. The aqueous phase contains organics such as alcohols and phenols and can be treated in a water treatment facility like Raiya mentioned before to remove the water from these organics. This water can then be reused within the process. You will be surprised that we can reuse as much as 96% of the initial water in this process. Next one is gases. The gas phase contains carbon dioxide and varying concentration of methane, carbon monoxide, and hydrogen, depending on the type of biomass used within the process. Carbon dioxide can be captured, and the remaining gases can be burned as a fuel to heat things within the process. Now, the last one is the solid phase. The solid phase mostly consists of char and ash, which are carbon-rich solids and can be used as fertilizers in our own switchgrass farms. It can also be used as a solid fuel or a catalyst. So overall, the char, gas, and aqueous phases are filtered and separated from the product stream, leaving us with just bio-oil that we want. Now, let's take a look at the impacts of this process on the 3 Ps, the people, planet, and prosperity. Starting with people, this project has a positive social impact as it will create more job opportunities across many sectors and will lead to increased economic activity and rural development in the region. Short-term construction and startup labor, as well as ongoing long-term operational jobs, will be sourced locally to build a relationship and sense of trust between the company and the local community. Looking at the planet, the project will help in exceeding Canada's current GHG emission reduction target under the Paris Agreement and achieve the goal of net zero emissions by 2050. The use of energy crops like switchgrass for energy production helps with carbon abatement. It also represents a cheaper alternative to fossil fuels while being extremely diverse in the species of plants that can be used for energy production. According to Pacific Northwest National Laboratory, it has been found that the GHG intensity of conventional fuels, such as gasoline and diesel, are 93.1 and 91.9 grams of carbon dioxide emissions per megajoule, respectively, whereas the resulting GHG intensity of the upgraded HTL biofuel is only 37 gram, which is a stark difference. Talking about the prosperity, according to International Institute of Sustainable Development, Alberta's sector has been an economic workhorse for decades, but its long-term market outlook is bleak. By the end of this decade, a combination of technological change, climate action, market forces, and geopolitics will drive a long-term decline in the sector, meaning its contribution to Alberta's future prosperity will be nothing like what it was in the past. Using bio oil for electricity production decreases this intense pressure on burning fossil fuels that we have. This gives us huge international competitiveness as well, as it highly decreases oil import from other countries. Large-scale production of greener fuels and electricity in our very own country will bring prosperity to us and our communities. We will keep our dollar and spend it on ourselves and for the betterment of our communities. We will have more money to invest on better hospitals, schools, infrastructure, and other societal needs. Since crops like switchgrass can be grown on marginal lands, this means more land for growing crops, which will result in more job creation for our farmers, hence rural development. Moreover, growing plants helps with carbon abatement, as we mentioned before. So it will be giving us and a future generation a much cleaner air to breathe in.
So, all this time, we talked about how amazing bio-oil is and what an easy solution it is to all our problems. But then now the question comes, why haven't we done this yet? The reason is lack of research and attention to this concept. So, fossil fuels are a natural source. It has been used for decades, and it is easy to extract. All our appliances, all our cars, pipelines, reactors, everything is made to support the fossil fuels. So as easy as it seems that bio-oil can be made from sewage sludge, from plants and things like that, it's not an easy oil to make, especially in large scale. So the reasons are it has corrosive properties, it has three phases, you're bringing in so much slurry in the beginning, and then you're converting it into oil, and then you're trying to separate the gas, the aqueous phase, the liquids, all from each other. It requires a lot of infrastructure developments. And reading different papers like in Steeper or Lysella, which are two big European countries which are trying to commercialize this into a large scale and then make all their electricity from just biocrude, it seems that the companies need large support from investors. It is important that we do a big research on it. There are more government support so that we can understand what kind of feedstock are giving us what kind of products, what kind of oils, what is the heating value of the oils, and what kind of how much amount of energy can be generated from that specific kind of feedstock. What is the ideal temperature, what is the ideal pressure, and how we can modify our current infrastructure. So our current pipeline, how can we modify our current fractional distillation columns, our reactors at the moment, so that we can be producing this biocrude in a large scale as far needed for our country's consumption need. So at this point, using bio-oil directly in jets, in cars, for our everyday use might be a little bit of a stretch given the property of the bio-oil, as we have previously mentioned, that the moisture content or the corrosiveness and stuff like that. However, we are technically going into an electrical world. So all the cars are turning into electricity, all the appliances we're using are trying to be electricity supplied. So if we can still use this biocrude to produce electricity, this will decrease an overall amount of fossil fuel extraction and the use in the world. So this was all for us. Thank you for listening. And if you have any questions, feel free to ask.
That's wonderful. Thank you. If you could maybe stop sharing the screen, we'll get into, so I know Kira has a question first. We'll go Kira first, and then we'll defer to some Q&A questions.
Thank you both so much for your presentation. I found it super, super interesting. I'm also a chemical engineer, so I'm excited about this kind of stuff. I had a couple of questions. You mentioned that solar panels are only like quite minimally effective or efficient, so you'd need lots of them. Have you thought about the intensity of like the location of solar panels? Because it would have to take up a lot of room if you need so many. And like where would you get that space? Because if like crops take up a lot of space too, and you can't cover them in solar panels, that defeats the purpose of the crops.
Right, can I take, or you want to go first?
Yeah. For the solar panels that we mentioned, we are trying to not have solar panels, and that is the reason why we are making this bio oil. So the things that we talked about solar panel was to give a perspective on how the solar energy is now used. So currently the solar energies are extracted in terms of solar power through solar panels. And we don't think, as we mentioned, that it takes a lot of solar panels to power a small plant, right? And it's only 15% to 18% efficient on a good day. And again, solar energy is not always available, especially in Alberta with the winters and 4 hours solar energy, it's tough. So we are basically suggesting that this solar energy can be captured through energy crops, because the crops are growing because of solar energy, and also taking in carbon dioxide in the process, so that we can harness this solar energy basically in the form of energy crops.
So when you speak about burning the biocrude to produce the electricity, that would release CO2, and I think you mentioned it could be captured. Have you thought about what or how you would capture it, and what would you do with captured CO2?
Yeah, I can answer this. So there is carbon dioxide that is released by the cogen electricity generation plant. And then there is carbon dioxide that is being released by the HTL plant itself. But we can capture it. We haven't really looked into how we are capturing it as of yet, but we can capture it. There are carbon capture plants out there. So we'll be trying to mimic one of them, and then we'll be doing further research. We have been researching on the HTL process itself, but those captured carbon dioxide can be used for the carbon credits. And then, yes, other companies can buy those, because this process itself is quite pricey. So other companies can buy those carbon credits from us, and then this way we will be making some of the money as well. So that's what we have in mind.
Also,
Sorry, go ahead.
Also, just to add on it, this carbon dioxide, like even if we cannot capture all of it, the idea when we are doing a carbon abatement ratio about how much carbon dioxide is taken in by the plant versus how much it's giving out when we're releasing it after the carbon capture, it brings the overall net carbon dioxide emission to be a very low amount.
That's really interesting. And we do have a question here, like now that you talk about marketing to companies and whatnot, how do you think biocrude or bio oil could become feasible on a commercial scale?
So commercial scale, so that is the reason why we're looking into making electricity than making like bio oil. So like there's been a lot of research, like a lot of people are saying that, oh, we can just easily use biodiesel for our cars, for our jets and stuff like that. But again, it's not possible as easily because this bio oil has moisture in it. So that is very difficult to separate this moisture. And in colder weather, like in Alberta weather, these moisture basically just freeze. And if it freezes in our engine, your engine is blocked. And it's and then other things like different pressures can separate it in your engine. So that's like not giving us the same amount of things, some amount of concentration, consistency as the fossil fuels. So at this point, just to make it much more feasible in real world aspect, the safety things and risks, taking those into consideration, the best would be to use this as biocrude and then burning that in a confined manner so that we can use the combustion energy to make electricity rather than commercializing it or transporting it to be used in cars and jet fuels as of yet.
So far, just to add on to that, so far all the research, like Raiya mentioned before, Lysella and Steeper, these big companies, the research that they have been doing, nothing has been, yes, I saw one of the questions where can it be done on a large scale? So far, what it has been done, like all the research has been just confined to lab space or a pilot scale, but not a commercial scale, because there are lots of strings that are attached with this kind of process. And to smoothen them out and to think about everything, it will take some time and more investment, definitely, and more attention to this this side of like solar energy capturing method. So once that is done, I think with time we will be able to find. And then again, like Raiya mentioned, using bio oil, which is corrosive and has moisture content in the make of cars that we have right now. We will probably need to change the material of construction as well for the engines, right? How we modified our cars for hydrogen fuel, we'll have to modify our cars for this as well. So that's the next step. That once we have finished researching on this first step on how to make it available and how we can store it in on that big of a scale, then that can be the next step.
Yeah, that's a great point for sure, and it's really cool to hear that you're doing some big things that need a little, love from the scientific community and from the corporate community to get things off the ground. It's really, really impressive. So we like to ask a couple of questions just about yourselves, because I know we have a lot of folks listening here who would consider like going into a similar field or studying similar things. So what made you choose your program or your school? And what is some advice you might have for somebody who's going to follow in a similar path?
So when I chose chemical engineering, I enjoyed, as cliched as it sounds, I enjoy science. And I enjoyed looking into like problem solving or troubleshooting, especially like you understand this. Maybe the first year it's always dry because you're just learning all the basic maths and stuff like that. But when you go into second year, your third year, you're basically learning a lot of small technical details about different designs and stuff, which I found was always interesting. I wanted to keep my field open. So as in my bio, I would say that I worked with like uremic toxin adsorption. So that is a completely biomedical field. And we worked with using how to improve dialysis, how to improve polymers to capture these toxins and stuff like that. On the other hand, I also worked with like oil sands, so partial upgrading, and then we're researching on how to make sustainable energy sources from different things. So basically, I felt like chemical engineering gave a very broad field. Also, my specialization is CPC, which is computer process control. So any kind of process control fields that we are doing, digitalizing the industry that we have right now, these things are also can be accessed, and we can easily change into those kind of fields if I wanted to work with that. It's a very fluid very fluid discipline too. So if you want to go into like data analysis in the future or do project management and stuff, that's also very easy to move into. So yeah, that's all right.
Yeah, so I think I always wanted to be in STEM. I grew up seeing my dad. He was a civil engineer in Indian Army. So saw that how his job was so impactful, and then he helped people. But then what I wanted was to be able to solve the small problems that we all face. And for some reason, I thought chemical engineering is the answer because it provides me with the skill set and the tools to be able to do that. And I won't regret choosing chemical engineering because it has given me those tools. And I'm working on other projects outside of school. Some of them are, and I basically in 10 years, I see myself as a social entrepreneur. And I think the skills that I'm learning right now, it is setting me up for that. So I can actually help solve everyday problems for many. We are privileged that we don't have those problems and we don't see them as problems. Something as simple as water, access to clean water. Those things are so basic that we don't really think about them, but there are so many people out there who are suffering with, they don't have access to clean water, and that's a basic necessity. So I always look at solving the small problems before looking at the big problems. And like Raiya mentioned, chemical engineering is a very broad field. I am specializing in oil sands. So I'm doing some research on that, but as a DRA, Dean's Research Awards, all my research in school was in materials engineering. So yeah, like I'm doing chemical specialization in oil sands, but then I am working on electrostatic atomization, which is a completely materials topic. So I think, yes, it is very fluid in that sense. And you can go in the biomedical field, you can go in pharmaceuticals, you can go in process control, you can go in oil sands. So you can really pave your path depending on what you like. So that is the one reason why I chose chemical engineering. And yeah, my experience so far, if I have to do it again, I won't change a thing. And I'm very satisfied with it. Yeah.
That's really cool. And then finally, our last question that we like to ask presenters. And I know we're pretty much out of time right now, but thank you everybody for sticking with us. A couple more minutes. What is your hope for resource sectors?
Yeah, I will say, I think Raiya did a good job in her last slide. We just need more attention. We just need researchers. Research is expensive. Putting time and the amount of time we have been putting along with our team on this project, it's insane. We are almost putting 40 hours a week along with our six courses that we are taking. And then I'm sure we have other things outside as well. So it takes lots of time, and you need skilled people to be working on this. We are just students, and if we can do this kind of research, I'm pretty sure there are like people who can do much better job at this. But then they need to be paid. Then we need to buy the equipment. So far, when we were doing this, the kind of research data that we were able to access was not really what we expected. We wanted to get more up-to-date data. And then if we are using the data from a lab and trying to scale it to a commercial business, there will be so many things that will go wrong there, right? It won't give you the accurate picture. So it's very important that we have some real life data. Maybe we have some pilot plans and some equipment. You can find a small filter to filter out char. Just to give you an example, if we have 3 phases going on in a separate, and then we have to filter it out on a small scale, we are okay. But if because we said HTL is high pressure process, to have that filter, and when things are going at such high pressure, we need a special filter. We don't have that. And we found out during this research that we just do not have a filter that can do this. And there are filters out there that are patented by the companies that are working on it. So, access to more research, access to more information so that this research can keep going on, and we can do it on a larger scale. So just more attention, more love. Yeah. I think that's what we need.
Yeah, as I'm not going to say anything extra with Robin, just the idea that the problem is with the amount of population we have, the amount of consumption that the world needs right now, to basically just stop one sector because any oil company, if you're starting it takes at least like 10 years to even cut even. So like whatever company that has started things, like for example, Suncor, Syncrude, they wouldn't want to change it so easily into, we're going to completely minimize our production on fossil fuels and increase and start doing on this. So it needs a lot of government support, a lot of government supplementation. The problem is, like, since it's such a huge change that's going to have to happen if we want to commercialize HTL, nobody really wants to take the step when there's like an easy solution at the moment. So like people try to wait till the very last moment to move into something better. And everything is already built to support this fossil fuels, it's a lot of work. And I think the main idea would be to have, like, if it's a more of a collaborative nature, like suppose US, Canada, two big countries working on it together. Like the US is trying to make everything by bio oil by the end of 2030. I highly doubt that's going to happen. But that's what their goal is. And if there's more support into doing that for one country, that the same process can be used for other places too. So it's like a lot of more collaboration when doing it rather than competitiveness. And honestly, a little bit of a greed is obviously there at behind all the products that we're making right now. So I think a lot more thinking about the future rather than the present would be better.
Yeah, that's a great response for sure. So many students are finding that their work is a little underfunded, and the money and the love that you need is always just a little out of your hands. So I'm hoping that comes along sometime for your project, because this seems really great. Thank you so much for presenting with us. That was brilliant. We really, really appreciate your willingness to share and your time today. And thank you everybody for attending and for asking questions. We appreciate the support.